So I'm going to talk about undefined behavior semantics in programming languages and why do we need undefined behavior semantics in programming languages. So let's look at this example, and this is on the left hand side column I am using an expression in a programming language, and you can also call it a high level programming language, and an example of a programming language is the C programming language. So I can have an expression which says x equals y by z. Now what does the programming language say what should happen if z equals 0, right? So that would be the divide by 0 error, that division by 0 should have some kind of error semantics because it's not a well defined result. And so the C programming language has many choices, and designers of the C programming language had many choices on what to do when z, or the denominator of a division operation, evaluates to 0. One option was that you just say, okay, you're going to actually explicitly throw an error to the programmer saying, oh, you tried to divide by 0, too bad, and I'm stopping your program. Another semantics could be that if it's a divide by 0, you just ignore it and you say it's as though it's a no-op. So you just say, oh, x is not even modified. Or the third option is that I can just set x to 0. And these are all kind of different alternatives that a programming language can take, because if something is not well defined, the language designer can choose what semantics he or she wants that suits his or her particular environment. And so while some languages will give you a well-defined semantics for such error conditions, for example, a high-level language like maybe Java or Python would say, oh, if you divide by 0, then I'm going to always throw an illegal or divide by 0 exception, let's say. And so that's a choice that some languages made. And then there are some other languages like C and C++ which said, oh, I'm not going to explicitly say what will happen here. I'll leave this choice to the runtime, to the implementation, to whatever is the environment under which this program is running. What does that mean? Well, if this program is running on an x86 machine, it can behave differently from if this program was running on a PowerPC machine, from if that program was running on an ARM machine, from if that program was running on an Arduino, or etc., right? So I mean, depending on the particular environment that you're running this program, this particular error condition could behave in different ways, and that's exactly what we call, that's roughly what we call undefined behavior. Some people, there's also something called implementation defined behavior, etc. But I'm going to kind of say what is undefined behavior very. I'm going to give you more examples to motivate the need for undefined behavior. So for example, one implementation could be, oh, if z equals 0, raise the divide by 0 exception. And if z is not equal to 0, do the computation x equals y by z. In the lower level assembly implementation, for example, in the assembly implementation, the divide operation may be implemented by the div opcode or something like that. And here's another implementation that says, oh, just do x equals y by z in the assembly program as well, and depending on what the assembly program semantics say, for example, the assembly program semantics may say that if you divide by 0, I'm going to actually generate a hardware exception and that's going to crash the machine. So in that case, it's the assembly semantics that basically win here. And at the C programming language layer, the programming language or the abstract machine says, I don't really care if that's an error condition, so anything can happen. I don't really know what may happen. It depends on the particular implementation, what it wants to do. For example, one particular implementation may want to explicitly raise a divide by 0 exception and let the programmer know. Another implementation may just crash the entire machine altogether, not just the program, but the entire machine. Yet another implementation could just ignore the error. And so these kind of semantics where you want to say that if a certain error occurs, anything can happen. These are called undefined behavior semantics, all right? So anything can happen semantics, all right? Also called catch fire semantics. So if there's a fire somewhere, which means, some exceptional situation occurred, then what should happen? That's what undefined behavior says. This is the catch fire semantics. Anything can happen here, and it depends on what the implementation is. Here's another example, and this is a very consequential example. Let's say x equals yi. So I'm just indexing into the array y using an index I. And this kind of an operation, which is just dereferencing memory at a certain offset, is very common in our programs, and different languages use different semantics for these kind of operations. For example, Java would say that if I was out of bounds or out of range of the array y, then it would explicitly throw the out of bounds exception or out of array exception, or let's call it just the memory exception. I'm just using Java as an example. There are many other high-level languages that would also do that. But this kind of explicit semantics of what should the program do, what should the machine do if the index was outside the range of the array being accessed, comes as a cost. The cost is the runtime cost of checking. So each time a programmer writes an expression like this, the machine or the compiler needs to basically check what is the value of I and how does it relate to the upper bound and the lower bound of y. And if it is out of bounds of y, then it needs to raise an exception. And so there is an extra 2 or 3 instructions that will get generated, and that would cause an extra runtime cost. But this is the choice that a language like Java made. On the other hand, a language like C doesn't want to pay this extra cost, because it just says most of the time the programmer is going to do the right thing. It's only some of the time that the programmer is going to do the wrong thing. And so it is performance inefficient to keep checking every time the programmer does yi, right? And so the C takes the other extreme view, which says I'm not going to check whether I is in the range of y or not. If it is in the range, I'm going to return the right result. If it is out of range, then it is undefined behavior. And once again, what is undefined behavior? Anything can happen, all right? Anything can happen. Either the program can crash, or the machine can crash, or an exception can be generated, or a segmentation fault. Depend if it's a Linux operating system, something else can happen. If it's a Windows operating system, something else can happen. Anything can happen. I'm not going to specify what happens if you do this wrong thing, where you basically exceed the bounds of the array index. For example, if it's possible that nothing happens, the programmer, neither a segmentation fault happens nor the machine crashes, it just returns a garbage random value from the memory space of the computer. All right, and this is actually happens because this is actually the basis of many security exploits, which are grouped under the category of buffer overflow attacks. And so a buffer overflow attack occurs because of these undefined behavior semantics in a language like C. And a language like C basically chooses to use undefined behavior semantics because it doesn't want to pay the performance cost of checking whether I belongs to the range or not and maintaining that state all the time. On the other hand, a language like Java does check all the time, and so these kind of security problems will not arise in a language like Java, but Java programs would consequently be slower than C programs typically. So here's one implementation. The first implementation actually checks whether I is out of bounds or not. If I is less than 0 or I is greater than or equal to y.size, then you raise a memory error. Otherwise, you basically return the value. And another implementation doesn't care. It just says yi, and it just adds I to the address of y and returns the result. And if I was belonging to the valid range, it would return the correct result. If I was belonging outside the correct range, depending on what y plus I evaluates to, it can either cause a segmentation fault or it can return some garbage random value. So this again falls in the domain of undefined behavior. Here is another example. X equals y plus z. Now this plus here is arithmetic addition in, let's say, in language like C. And we know that y and z, and let's assume y and z are signed integers. So y and z are not infinite integers, right? Y and z are, if they are, it's maybe 32-bit integers or 64-bit integers. So let's assume they are 32-bit integers. So what happens if y plus z overflows the 32-bit value? What should happen in that case? Now, one option here is that the C abstract machine could have said, whenever you do y plus z and it overflows and there's a 33rd bit which is non-zero, then you just discard that 33rd bit and pretend as though that 33rd bit was 0. These are called wraparound semantics. And that's the typical kind of implementation that you would find on a 2's complement machine. And this kind of a wraparound semantics can be, can be represented using this circled plus. So y plus operator circle z, which basically, plus operator basically explicitly says that it's a 2's complement addition with wraparound semantics, where you discard a 33rd bit in case of an overflow. But there are some machines which do not use 2's complement. Maybe they use 1's complement. Maybe they use some other representation. And so the C designers didn't want to basically explicitly say what should y plus z evaluate to. For example, there could be a machine which implements saturating arithmetic. So it may say that if it overflows, then the value that you will get returned is not the wraparound value, but actually the maximum value that 32 bits can hold, right? So if you basically say, 2 to the power 32 minus 1 plus 1, then you don't expect the answer 0, you actually get just 2 to the power 32 minus 1, because that's the saturating value. That's the maximum value that you get, and that's called saturating arithmetic. And so the C designers, the high-level language designers, once again left it as undefined behavior. They said, oh, by the way, if y plus z happens to overflow, then it's an error condition, it's an undefined behavior, and anything can happen, including the fact that the machine can crash, or it can return a wraparound value, or it can return a saturating value, or something else can happen. Right? So undefined behavior basically means that this is an error condition. It shouldn't happen, but if it happens, then all bets are off, and I cannot make any guarantees on what your program will do in that case on this abstract machine of the C programming language. So why do we need undefined behavior semantics? I think I've already motivated this by comparing C and Java. One language doesn't use undefined behavior semantics, it uses well-defined error semantics, and the other language like C uses undefined behavior semantics. And that allows the C compiler to generate faster code for the C program, and Java programs are typically slower in comparison. So let's look at some examples, what kind of transformations or what kind of compiler optimizations does undefined behavior or UB enable or facilitate. So let's say I have int n, some variable, and I'm evaluating n somewhere here, and then I have a loop which says for int I equals 0, I is less than n plus 1, I plus plus. Now, I'm already storing n, let's say, in a register, and now for this particular loop, I have to compute n plus 1 in a separate register and keep comparing on every iteration. So one obvious kind of, optimization that comes to mind here is that you can say, oh, just convert I is less than n plus 1 comparison to I is less than equal to n. And you can imagine that this should be correct. And question is this legal? And the answer is, well, imagine what will happen if n was equal to int max, right? So if n was equal to int max. So int max is, let's say, if on a 32-bit machine, that would be 2 to the power 32 minus 1. So all ones, right? And so if n equals int max, then the first program would be int max plus 1. And if I assume wraparound semantics, that would be just 0, because 2 to the power 32 minus 1 plus 1 would be 2 to the power 32, and that won't fit in a 32-bit number, and that would make it to 0. And so the for loop would look like I equals 0, I is less than 0, I plus plus, which means the for loop never executes. On the other hand, look at this loop. Here it would be I equals 0, I is less than equal to int max, I plus plus, and in this case the loop will go on forever. It's actually an infinite loop, because I goes from 0 and keeps incrementing till it becomes int max, and then it increments again, and then it becomes 0 again. So I would always be less than equal to int max, and so this loop goes on forever. So these two programs are completely different in their observable behavior, in the behavior that they produce. And so this transformation will not be legal if I assume one particular semantics of the addition operation, which is the wraparound semantics or the 2's complement semantics. But fortunately, this transformation is very common. It's widely used, and it's widely used because it's a legal transformation in C. Because C says that signed integer overflow is undefined behavior. It says that if n plus 1 overflow, that would be undefined behavior, and if it's undefined behavior, anything can happen. So if the programmer has written code where the program actually can potentially do int max plus 1, then that program itself is illegal, and so the compiler can do whatever it likes, and in that case it can also kind of convert that into an infinite loop, and so we are okay. All right. In other words, it should never happen from the compiler's perspective that the signed integer overflow occurs. So signed integer overflow should never occur, and if it occurs, that would be illegal. And this is exactly what the undefined behavior semantics or UB semantics state. Here's another example, and this is an example for type-based strict aliasing semantics. So let's say I have two arrays or two pointers. One is an integer, a pointer to an integer value or a set, an array of integer values. Another is a pointer to an array of float values. And I have this loop which says for int I equals 0, I is less than n, I plus plus, bi plus equals star a. So in this case I am dereferencing a. In this case I am dereferencing b at a given offset I. And now the question is, can I improve this loop? Can I make this faster? Because I have two memory accesses on every iteration of the loop. But one of those memory accesses is going to be the same memory access, which is star A. And so can I change this to, take star A into a register, let's say R, or some kind of, easily accessible value location. Let's say R is a register in this case. If I'm talking about assembly instructions on CPUs, then for int I equals 0, I is less than n, I plus plus, bi plus equals R. So this is just, I just kind of did some loop invariant code motion and just kind of cached the value and then kept using it over and over again. The question is this legal? And the answer is this is not legal if it is possible for bi to actually alias with a. Alright, so if bi could kind of point to the same location as a, then across different iterations it's possible that one of these bi's actually writes to a, and so that means I should keep reading a over and over again, because it's possible that I modify star a in one of these iterations, and if I modify it, then I need to refresh that value. And so if I do this, then I'm not going to be refreshing the value on every iteration, because so that would be these two programs would be inequivalent, because once again, if bi can alias with a, then these two programs are inequivalent, because a's value can change, star a's value can change across because of the write to bi. However, the C programming language states that if there's code like this, then because these are two different types, this is a floating point type, b is referring to a floating point type array, and a is referring to an integer type array, then it would be undefined behavior if b and a alias to the same location. It shouldn't ever happen that I'm basically dereferencing an integer type value where a float type value could have been present. And this kind of type-based strict aliasing is basically meant to accommodate the fact that different compilers or machine environments may use different representations of different types. For example, a floating point type could be represented either through IEEE 754 standard or something else. And I don't want to make assumptions on what they are. And if the programmer is basically kind of mixing and matching the same region of memory, sometimes using it as a float and sometimes using an integer, then that would be undefined behavior. And in other words, that should never happen in a legal program. When I say that should never happen, it doesn't mean that the compiler will flag it or compiler will generate an error, because compiler cannot check everything. So what the language designers basically did was they said it's the responsibility of the programmer to ensure that there is no undefined behavior in their program, because the compiler cannot check everything, right? For example, compiler cannot check whether I belongs to the range of B or not. In general, that's an undecidable problem. And so what the designers in case of C decided was that we just leave that responsibility to the programmer. In the case of Java, they decided that we're going to do runtime checks to make sure that the programmer is not doing the right thing. So in this case, this transformation is legal if you make the type-based strict aliasing assumptions which are based on the type-based strict aliasing undefined behavior semantics of the C abstract machine. Here's another example. So let's say I have an array A which has size 256 and another small array B which has size 1, and I initialize a pointer P to A, and then I have a loop from I equals 0 to n, and I'm also incrementing P every time, and I'm saying star P plus equals B0. This is very similar to the example that we've seen before, but here instead of actually explicitly dereferencing AI, I'm actually maintaining another pointer P. And in this case, the semantics are that because P is based on A and I'm incrementing P any number of times, irrespective of how many times I increment P, it should never happen that P actually points outside of A. In other words, what the C language says is that P is based on A. P is based on A, and because it's based on A, it should never exceed either underflow or overflow the range of A. And so because of that, I can actually do this transformation, which is I can basically cache the value of B0 into a register R, and instead of star P plus equals B0, I can do star P plus equals R. Why is it legal? Because why is it legal to do so now? Because I know that P cannot alias with B0, because P should belong to the range of A. And the range of A is basically this range from 0 to 255 of the A array, and it can never get into B. And if it gets into B, that's undefined behavior, so the compiler doesn't need to worry about that. The compiler can just assume that the programmer has written the correct program, which does not have UB, or it's a UB-free program. So this answer is that this is legal under the based on semantics in C. Finally, everything that we have discussed so far is basically at the programming language level, but most of our transformations, like all the optimizations that I described in the previous slides, are actually usually done at the intermediate representation level. So how does one capture the PL level semantics at the IR level? So first of all, you basically add instructions to your IR which basically mimic the behavior of the instructions at the C language. For example, LLVM also has a divide instruction or the divide opcode, and that can also trigger UB. So LLVM also has its own UB semantics, and LLVM's code will also trigger UB if you do a divide by 0. And so that there becomes, because of these semantics in LLVM, it's easy to translate from C to LLVM. Now you may say, okay, but that's just for C to LLVM. What if I want to translate a Java program to LLVM? Well, if you want to translate a Java program to LLVM, what will happen is that in the generated LLVM, you would have explicit checks for that particular index variable before you actually do for that denominator being not 0 before you actually do the division operation. Also, when another example that I used was arithmetic overflow or signed arithmetic overflow. I'd like to point out that in C, it's only signed integer overflow that is undefined behavior. Unsigned integer overflow is not undefined behavior, and this is just to provide flexibility to the programmer, so that if the programmer wants to use explicit wraparound semantics for his or her variable, then he or she should use the unsigned variable and not the signed type for the variable. Okay, in any case, there are three flavors of the addition instruction or addition opcode in LLVM. One is just the plain addition y plus z, which would have, let's say, the wraparound semantics. So if it overflows, then you just discard the 33rd bit or the most significant, the overflow bit. The other is the no signed overflow variant of the add instruction. So NSW stands for no signed overflow. Add NSW y comma z can assume that y plus z will not overflow, and if it overflows, then it is UB. So in this case, just like C, UB if signed overflow. Okay, and the other kind of nice thing about LLVM is that it also gives an unsigned overflow variant of this instruction. So this is NUW, so no unsigned overflow, and that is UB if unsigned overflow. Recall that I said that in C there is no notion of NUW, or C only supports signed integer overflow UB. Unsigned integer overflow is actually wraparound in C, but because LLVM caters to more languages than C, it actually treats signed and unsigned more uniformly, and if somebody wants to implement unsigned integer overflow, then they can use the NUW opcode in LLVM. So basically what's coming out is that whatever are the semantics in the programming language are also being reflected in the IR to be able to reason about the transformations, kind of transformations that we discussed in the previous slides. And finally, another example that I used was based on relationships based aliasing reasoning in C, and the same kind of reasoning can also be done at the IR level. So when you're doing the transformations, you already know which language did this LLVM come from, and based on that you can basically make assumptions on what is based on what, and based on that you can do the transformations. Overall, when you kind of move from one abstract machine to another abstract machine, let's say you move from the C abstract machine to the LLVM abstract machine, you may lose some information. And so in these, all the three things I described, I'm basically saying that, the programmers or the compiler developers have made good efforts to ensure that information is not lost. For example, it's possible to basically use these custom operators or to implement the based on relationship based reasoning, but some information is lost in any case. And I'm not going into details, but it's obvious that whenever we lower one piece of syntax to another piece of syntax to a lower level syntax, then not all programming language UB semantics are captured, and some programming language UB semantics are forgotten at the IR level. What are the implications of forgetting some UB semantics? Well, it doesn't make the program any wrong. It just makes optimization, it just kind of kills some optimization opportunities. So if the translation from a high level syntax to a lower level syntax forgot some UB in the program, in other words, for example, when I was doing arithmetic, maybe I just used add y comma z instead of using add nsw y comma z, then what I'm not making the program any wrong. It's still the correct program, because I've just made one particular choice of a wraparound semantics in case the error condition occurs. But the problem here is that you may have lost some optimization opportunity.